Early concepts of light and matter. In the late 19th century, physicists were grappling with the nature of light and matter. The phenomena of blackbody radiation, where objects emit radiation depending on their temperature, couldn't be explained by classical physics. Similarly, the photoelectric effect, where light shining on a metal surface ejects electrons, challenged classical wave theories of light. These phenomena hinted at the need for a new theory. Planck's quantum hypothesis, 1900. Max Planck's quantum hypothesis proposed that energy is quantized, meaning it exists in discrete packets rather than being continuously distributed. He introduced the Planck constant, h, to describe this quantization. Planck's theory successfully explained the observed spectrum of blackbody radiation, but he initially regarded it as a mathematical trick rather than a fundamental physical principle. Einstein's explanation of the photoelectric effect, 1905. In one of his groundbreaking papers of 1905, Einstein proposed that light is composed of discrete packets of energy, called photons. He used this concept to explain the photoelectric effect, showing that the energy of ejected electrons depends on the frequency of the incident light rather than its intensity. This work earned him the Nobel Prize in Physics in 1921. Bohr's model of the atom, 1913. Niels Bohr proposed a quantum model of the hydrogen atom to explain its spectral lines. In Bohr's model, electrons orbit the nucleus in quantized energy levels, and transitions between these levels correspond to the emission or absorption of photons. Bohr's model successfully explained the Rydberg formula for atomic spectra but relied on ad hoc assumptions and lacked a theoretical foundation. Wave-particle duality, 1924. Louis de Broglie proposed that if light, traditionally considered a wave, could behave like particles, photons, then particles such as electrons could also exhibit wave-like behavior. He introduced the idea of matter waves, suggesting that particles have a wavelength inversely proportional to their momentum. This wave-particle duality laid the foundation for understanding the behavior of particles at the quantum level. The uncertainty principle, 1927. Werner Heisenberg formulated the uncertainty principle, which states that there is a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, can be simultaneously known. The uncertainty principle arises from the wave-like nature of particles and fundamentally challenges the classical notion of determinism. Schrödinger's wave equation, 1926. Erwin Schrödinger developed a wave equation that described the behavior of quantum mechanical systems in terms of wave functions. Schrödinger's equation is a central tool in quantum mechanics, providing a mathematical framework for predicting the behavior of particles and systems at the microscopic level. Matrix mechanics, 1925. Heisenberg, along with Max Born and Pascual Jordan, developed matrix mechanics as an alternative formulation of quantum mechanics. Matrix mechanics describes physical quantities in terms of matrices rather than wave functions. Initially, it appeared different from Schrödinger's wave mechanics, but later it was shown to be equivalent, providing different but complementary perspectives on quantum phenomena. The Copenhagen interpretation, 1920s. The Copenhagen interpretation, formulated by Bohr, Heisenberg, and others, emphasizes the role of probability and measurement in quantum mechanics. According to this interpretation, a quantum system exists in a superposition of states until it is measured, at which point it collapses into one of the possible states. The interpretation highlights the role of the observer and the limitations of classical concepts in understanding the quantum world. Wave function collapse, 1930s. The concept of wave function collapse, inherent in the Copenhagen interpretation, posits that when a measurement is made on a quantum system, its wave function collapses to a specific state. This concept has profound implications for our understanding of reality, consciousness, and the nature of observation in quantum mechanics. Quantum entanglement, 1935. Erwin Schrödinger introduced the concept of quantum entanglement, which occurs when the quantum states of two or more particles become correlated in such a way that the state of one particle cannot be described independently of the state of the others. This phenomenon, famously illustrated by Schrödinger's thought experiment involving a pair of entangled particles, challenges classical notions of separability and locality. EPR paradox, 1935. The EPR, Einstein-Podolsky-Rosen, paradox was proposed by Einstein, Podolsky, and Rosen as a thought experiment to challenge the completeness of quantum mechanics. They argued that if quantum mechanics were correct, it would entail spooky action at a distance, where measurements on one entangled particle could instantaneously affect the state of another, regardless of the distance between them. Development of quantum field theory, 1920s to 1940s. Quantum field theory, QFT, emerged as a framework for combining quantum mechanics with special relativity, enabling the description of particles as excitations of underlying quantum fields. This led to the development of quantum electrodynamics, QED, by Feynman, Schwinger, and Tominaga, which successfully explained phenomena such as the Lamb shift and the anomalous magnetic moment of the electron. Dirac equation, 1928. Paul Dirac formulated a relativistic quantum mechanical equation describing the behavior of fermions, particles with half-integer spin. The Dirac equation predicted the existence of antiparticles, such as the positron, and laid the foundation for the development of quantum field theory. It unified quantum mechanics with special relativity and provided a framework for describing the behavior of fundamental particles. Quantum mechanics and statistical mechanics, 1930s to 1950s. Quantum mechanics was successfully integrated with statistical mechanics, leading to the development of quantum statistical mechanics. This theoretical framework allowed physicists to describe the behavior of large ensembles of particles at the quantum level, providing insights into phenomena such as phase transitions, Bose-Einstein condensation, and the behavior of quantum gases. Bell's theorem, 1964. Physicist John Bell formulated a theorem that placed constraints on local hidden variable theories, which attempt to explain the apparent randomness of quantum mechanics by positing underlying variables that determine the outcomes of measurements. Bell's theorem provided a means of experimentally testing the predictions of quantum mechanics against classical theories and has since been confirmed by numerous experiments, ruling out certain types of local hidden variable theories. Quantum computing, 1980s present. Theoretical and experimental work on quantum computing has progressed rapidly since the 1980s. Milestones include Peter Shor's algorithm for factoring large numbers exponentially faster than classical algorithms, which has significant implications for cryptography, and Love-Grover's algorithm for searching unsorted databases quadratically faster than classical algorithms. These achievements demonstrate the potential power of quantum computers for solving certain types of problems more efficiently than classical computers. Quantum information theory, 1990s present. Quantum information theory has emerged as a field focused on the study of information processing using quantum systems. Researchers explore the unique properties of quantum mechanics, such as superposition and entanglement, to develop protocols for tasks such as quantum cryptography, quantum teleportation, and quantum key distribution. Quantum information theory has applications in secure communication, quantum computation, and fundamental tests of quantum mechanics. Experimental tests of quantum mechanics, 20th and 21st centuries. Advances in experimental techniques have allowed for increasingly precise tests of quantum mechanics and its foundational principles. These experiments confirm the predictions of quantum mechanics and rule out certain alternative theories, providing strong support for the quantum mechanical description of nature. Examples include tests of Bell's inequalities, violations of local realism, and demonstrations of quantum entanglement and teleportation. Challenges and open questions, ongoing. Quantum mechanics continues to present conceptual challenges and open questions. These include the nature of measurement and the role of the observer in quantum systems, the interpretation of the wave function and the implications of wave function collapse, and the quest for a theory of quantum gravity to reconcile quantum mechanics with general relativity. Research in these areas is ongoing, with the aim of deepening our understanding of the fundamental nature of reality at the quantum level.